wave assignment we do tonight? I don't know if I missed it, but can you help with the RMS value?
The final, I'm sorry?
Well, our EM wave assignment we do tonight, I need help with the RMS value.
Oh, yeah. We better do it right now before I forget. I thought did I change it? Let me see here. No, I guess I didn't. Let's double check. Okay. Yeah, that's not a problem. I can do that. Skip 5. Just skip it. In fact, yeah, you know what? I have a lot of RMS stuff in here, and I just completely skipped it. What's the easiest way?
Are you saying 5 from magnetic induction?
No, for the EM waves.
Okay.
No, I'm just looking at it going, how much time are you putting in it right now, Isaiah?
I just like looked through it.
Does everybody just look through it?
Yeah, I just try to see that.
Because I can see that like 6 of you have actually opened it. Oh, but good, but nobody's actually, okay. Well, man, there's an overachiever in here. I'm not going to call you out, but there's an overachiever in here. But what's Q1? You got Q1. How did you get Q1? I haven't even talked about Q1. Yeah, how'd you get Q1? Impressive. Do Q3. I think, in fact, you know what? I'm going to do something else. I'm just going to cancel. Don't even bother with it. Just pretend that it's not there. Just don't even bother with it. I'm going to move the one question that I'd be interested in having you do. I'm going to move that to the next homework set, but don't even bother looking at it. All right. So the only question that I'm going to have you do on that is, okay, first of all, let me hide it so that you can't see it. And yeah, let's just take this whole thing away. Give me 2 minutes here. And what am I going to do? I'm going to hide this from you so that you can't see it at all. And it is no longer in your, okay, so we'll hide that. Now the question is, how many, oh, good gravy. Really? Man, there's overachievers in here. So the one question, sorry, I'm changing the homework assignment just ever so slightly here. Spherical mirror, plane mirrors, okay. Add a question from the question bank. Un momento, por favor, because I just... EM waves. Okay, you're good. Here you go. Enjoy your Monday evening. You dropped like an F-bomb when I was walking into the room, so you must not be having a good Monday. It's not me, is it?
No.
It's not this class, is it?
No.
See, physics is awesome.
I hate Franklin.
You what?
Franklin College. I hope to go out of business.
Theoretically speaking, like 20% of the colleges need to go out of business.
Yeah, it's really good.
Yeah. It's a bad day. Okay. Yes. Thank goodness it's not Manchester. What's up?
Oh, so you just hated the entire assignment?
Yeah. You shouldn't even be able to see it anymore. Yep. And I'll move it out of the grade book as well so that it just disappears. So the one question that I'm particularly interested in, I moved to the next homework set. So, and namely it's the speed of light thing. So if you look now, yeah, you'll see that speed of light thing. And it's essentially the Fizeau and the Foucault apparatus that I discussed on Friday. It's just actually having you relate the speed of light to the angular frequency of the mirror. So of course, the way that they did it was they didn't know the speed of light, but they knew the angular speed of the mirror. The question assumes that you know the speed of light and asks you to find the rotating mirror. So it's the same idea, so you can get an idea. And it's not a complicated mathematical derivation or anything. It's just a little bit of geometry. So I thought, oh yeah. And if you ever get excited, we have a similar apparatus in the physics lab. So if you wanted to actually measure the speed of light, we have an apparatus that allows you to do it. So, yeah. Okay, thank you for raising that point. Boom, Monday night's clear. Other questions? Party on, Bill. Party what? I said party on, Bill. What did you say? Wait, is his name Bill in Wayne's World? Yeah, I was thinking Bill and Ted. Like, party on, Bill, party on, Ted. Excellent. See, I've never actually seen Wayne's World. Okay, so now I've got a cultural assessment, or a cultural assignment for today. Go and watch Wayne's World. I watched Napoleon Dynamite and couldn't stand it, so I assume Wayne's World is similar.
I think Napoleon Dynamite is actually a little bit educated.
Yeah, okay, it's Wayne's World. Yeah, but I should watch it once. Okay. Yeah, rock and roll. Geometric optics. So we'll qualitatively kind of start going through some of this stuff. And namely, I'll give you Snell's law at some point, which is quantitative, but really the quantitative portion comes in later with like the thin lens equation and some other stuff. So there's a couple of extra things that I've left off on here. But this will essentially get us going for the rest of the time. And depending on how fast or how comfortable we are with the material, then we can maybe move into some physical optics, but that one is just kind of a question mark. So I've already, you can't see that assignment or anything, and if we so happen to get far enough, that's great. So yeah, geometric optics. There's not much to say about this. Let's keep going. Of course, oh yeah, fancy little image there. So, okay, this doesn't seem to want to work. Let's try that again. There we go. So we'll start off. There's two types of geometric optics that we're going to have to deal with. You're probably already familiar with them. One of them being a mirror. And so we need to talk about how does light interact with a mirror. And then the second one is how does light interact with lenses. And so I just want to build up a conceptualization of what's going on there. So we'll start off with mirrors. And you have one rule of the game. Well, okay, it's two. So the first thing is that anytime you're dealing with a mirror, actually a lens as well, there's going to be something called the normal. So you have to, anytime you're dealing with a mirror or a lens, you have to identify what the normal is. That's a fancy word for saying the line perpendicular to the surface. So anytime you're dealing with lenses or mirrors, you are thinking about the line perpendicular to the surface. Okay, so if this is the surface of a mirror, we would draw in a normal, something like this. It's a mirror or a lens for that matter. And all of the relationships that are given for mirrors or lenses, they're always measured with respect to the normal. So that dashed line is the line that we measure all of our angles from. I have no idea why that's the case, but that is. So anytime that you're dealing with Snell's law, or anytime you're getting an equation that has angles in it, it's always those angles are with respect to the dashed line. Yeah, I don't know why. Rule of the game for mirrors. The angle in equals
Go out.
the angle out. Boom, done. Pretty boring, really. And sometimes people will say it's the law of reflection, but that's basically it. The angle in is equal to the angle out. And again, notice I've measured both of these angles with respect to the normal of the surface. The law of reflection. It's pretty boring, really. And we're done for the day. Okay, have a good afternoon. Yeah, I mean, I wish I had more to say about it, but that's pretty much it. Yeah. So question for you. Might as well just get some practice. So, there you go. Here's a surface. Say it's the surface of a mirror. Draw the reflected waves. So 3 light rays strike the surface of a mirror, shown below. So I've given you a couple surfaces. Go ahead, draw the reflected rays. Go for it. Yeah,
Is there any way you can turn one of the lights off?
I can turn all of them off.
One is okay.
Siri, turn off lights. Oh, nuts. Oh, that was worth a try. Yeah, I can. You need more contrast on the board? Or is it just the overhead brightness in general?
Yeah, the lights are just turning on.
There we go. Is that better?
Mhm.
Is that too bright, or should I? Yeah, no problem. Darn Franklin College. It's not meningitis, is it?
No, I just
Your
have,
neck doesn't hurt, does it?
I have a concussion.
Oh, the baby.
Yeah.
Okay, now I understand the Franklin College comment.
Yeah.
What's the sport?
Football.
Oh, okay.
Mm.
Hopefully Brandon went the back for you.
Mm, yeah, sure.
And you just start swimming this thing. Okay. Okay, yeah. I'm more sensitive about these things. I mean, rightfully so. Right, yeah. Yay, nay? I just figured, yeah, what the heck. And in some sense, I mean, like, there's not really much more to say about it. Yeah, I mean, here we go. You can draw a normal. I mean, if you're really disciplined, what you do, you could probably draw a normal to the surface for each of these suckers. So let's see here. Let me get a normal here. Oops, slide it over. You could probably draw a normal to the surface for each of these suckers. So right here, probably have something that's like this. You know, the normal, because that surface is tilted, it's a little bit more tilted. And then right here, you probably have something like this again. Oops, sorry, that's extra long. So then you can kind of get an idea, like visually, okay, well, there's the angle, so the reflected wave should go off like this. Whereas you notice this one, the angle is smaller, and so the reflected wave should go off in some other direction. And then, you know, again, angle. And you just keep going. I assume you kind of had something like that. Yeah. Now, I guess the place where I find this most interesting is it used to be 5 years ago or even 10 years ago, this was more interesting. Right? Nowadays, it's not so much because you tend not to walk around with these things anymore. I can't tell you how stoked I was when I finally, I wasn't stoked about buying a new car, a new used car. And that's not a stokey kind of moment. What I was stoked about was when I opened it up and there was a CD player still in it. Yeah? You guys don't get stoked about CD players? Oh, I was stoked. I was like, all right. And bummed down the road listening to Odessa and Daft Punk. Huh? Yeah. But this is exactly the technology that CD player uses. How does the CD player actually work? And what's the inner workings of a CD player? You pop it in and boom, it just goes. It spins. Okay, so number one, it spins. And there's a laser that reads it. Well, how does the laser read it? Oh, and incidentally, how do you damage a CD? You scratch it. Okay, so you know that you pop it in, it spins. You know there's some sort of laser in there, and you know that if you scratch it, then it doesn't work anymore. Or you start getting a skip, right? You get some sort of skipping action. Well, what's going on? Imagine for a second that this is the surface of a CD. Right? And furthermore, now the laser stays stationary. Okay? If you want to scan different parts of the CD, you have to spin the CD so that the laser sees a different part of it. Okay? Now, I've done it in terms of spatial, but you can think of it as being at one spot and the CD moving instead. Okay? And what else do you do? Well, that's one thing. You have the laser coming in. The second thing that you do is you set up your detector. Okay? And you set up your detector at a certain angle so that when the laser comes in, it bounces off the smooth surface, it goes to the detector. And the only time it doesn't go to the detector is if you put a pit on the surface of the CD. When you angle the surface of the CD, I did it as an angle, the laser gets reflected to a different position, it doesn't hit the detector, and the detector says, okay, no CD, or no light. And this translates into, for lack of a better word, I'll say Morse code. It's not really Morse code, it's a binary, it's on, off. It turns into a digital signal. Light, no light, which then the computer converts into a sound, and then you get it through your speakers. Right? So we listen to one more time. Or aerodynamic. Bangarang?
Those two were in Discovery.
Huh?
Those two songs were in Discovery.
Yeah. Well, I was thinking, I went to Bangarang because that's Skrillex. I figured, okay, since you guys don't seem to be Daft Punk fans, go to Skrillex. Ghosts and stuff? Not Dead Mouse fans either? Okay. Copeland, fanfare for the common man. We're just sitting there bumping to Copeland, okay? But this is exactly what's going on. In fact, if you take a zoomed in picture of a CD, this is the surface of a CD. Okay? And what you have pits, you have smooth surfaces where the laser hits and sees the light. You have pits where the light isn't reflected to the detector, it's reflected to some other angle. And based on that, the CD can take this physical inscription and translate it into a digital signal that then goes through your speakers. I mean, it's essentially no different than a record player, right? You can see the 45s or the 33s, right? The only difference is that instead of having a needle jostling back and forth to give you the signal, it's just a laser bouncing off the surface to give a signal. And then the last thing is that, of course, the laser stays stationary, but you move it left or right to read further out on the disk. Which also tells you why a scratch ruins your disk. Right? Because when you scratch, what you've done is you introduce a new pit, you put a scratch in there. Now you're introducing a new pit or a new surface, a new angle on the surface that reflects the laser to a different location, and so that buggers up the whole thing. Okay. No? Yeah? That's all. It's just based off of this law of reflection. Put the detector at one spot, shoot a laser, and there you go. Yeah. Same thing. DVDs. Exact same idea. The only thing that's changed between a CD and a DVD, which one can hold more material, more information?
Curious.
Which one do you think takes a lot more storage space? 12 songs on Discovery? Or, I don't know, an audio-visual representation of Tron? I'm sorry? The DVD. The DVD can store more information, right? You get the full soundtrack plus pictures. Right? Let's face it, Tron was just a 3-hour-long Daft Punk video. Let's be honest about this.
Are you talking about legacy or the original?
Legacy. Yeah. right? Not only do you get the music, but you also get the pictures. Well, if you ever notice, you compare the size of a CD to a DVD, if you notice that they're the exact same size, I mean, they're, right, not by accident, I guess. So what changed? How can you get more information on a DVD as opposed to a CD? Why? The disc stays the same size, but you get more information on there. Smaller holes, you pack the holes closer together. So what happens on a DVD is that the distance between the holes gets smaller, both in terms of this way, but also this way. So if you can pack more rings of dashes and dots on your disk, you can store more information that way. What does that mean about the size of the laser on the disk? If you pack the lines closer together, what do you have to tell me about the spot size of the laser on the disk?
The diameter decreases.
The diameter decreases, right? So for a CD, the CD technology that's been around since what, the early 90s, you're just developing lasers, the spot size of the laser was rather large, which meant that when you were doing these dashes and dots on the surface, you had to have them further apart in physical space, so that when you shine your laser dot, you didn't accidentally pick up the adjacent lines on the reflection. Well, what happened, a couple of things. First of all, we got better at making lasers and focusing them, making cheaper lasers. That allows us to make a smaller spot size on the disk, and that allowed us to pack the information closer together. So then all of a sudden you get, something like DVDs, which can hold, I think a CD was like 700 megabytes. I think a DVD is up around a couple gigs now, like 2 gigs or something, give or take. You can pack almost 3 times the amount of information on the same size disk. Of course, nowadays, DVDs aren't even the thing, right? Now it's Blu-ray. Again, the same idea. Basically what happens is they get better at focusing down the laser, and so they can pack more information on. And they have things like double layered now. So what happens is that, okay, so you got CDs, you get DVDs, so you change the wavelength of the laser, and you can actually get it focused down to a smaller spot size. Incidentally, if you're familiar, the same kind of ideas hold with microscopes. There's limits to how small you can focus the light on a microscope, but if you use if you're using the fluorescence microscopes, you're using some of the same ideas here. Anybody use the fluorescence microscopes? Okay, I don't know if anybody does fluorescence in biology or not, so I just thought I'd ask. Okay, yeah, huh? I think that there's at least one fluorescence microscope. And the reason I say is because I think Dr. Pretorius had a camera for it, or was buying a camera, an Olympus camera for it, if I recall correctly. So yeah, essentially what's going on is with the CD, and then the DVD, and then later the Blu-ray, is that you can focus the spot into a smaller size, which means you can pack more information on it. Now I gotta double check. I think like the 4K stuff, I think that they basically hit the limit of how small they can package it, like get the lines together, but now I think you can actually do double layers. So you have like a top layer of dots and dashes, but then you can do a layer underneath, so it's like double layered. I have to double check that, but the general idea still holds. You're basically bouncing a layer off the surface, a laser off the surface, looking for the reflection to give you the digital signal. No? That's all I have to say about that. Like I said, it's kind of going out because like nowadays you don't do physical copies anymore, right? You just like jack your CD player or your phone into the car and listen to MP3 files. That's kind of going the way of the dinosaurs, but I don't know. I always find the sound quality better on a disc.
That's the only physical stuff.
I love physical stuff. But anyway, where do you guys buy your music from? I'm just curious. Is it iTunes? Okay. Like, I don't have an iPhone, so like, I kind of shy away from iTunes, but I don't like Amazon either. So I'm like trying to find a good place to buy music from. I want like the high quality FLAC files, even though I'll never use them. Lossless, I don't want that 320 megabytes per second garbage. I want the full blown. Okay. So, yeah, and of course, your DVD writers or your Blu-ray writers, essentially what they're doing is they're etching the surface of the disc. I have no idea how the rewritable discs work. My guess is that, well, okay, I can take a guess. Certainly the single-use ones, you're literally etching the surface with the laser. So there's a high-powered laser, when you burn the CD, it's etching the surface so that when it can be read again, it does that reflecting thing. I assume that the rewrite stuff basically has multiple layers, and so when you want to rewrite it, you just basically etch the entire top layer and then restart again. So it's kind of like erasing the top layer and then re-etching. So my guess is that those rewritable ones, you can only do it a certain number of times before they go bad. And I don't know if you've ever experienced this, but like trying to put a rewritable CD into a CD player, sometimes they recognize it, sometimes they don't. Like I've always, again, that depends if you play around with the physical copies. But Blu-rays would be the same way. I think they do writable Blu-rays now. Is that right? I know DVDs they certainly do. I think Blu-rays they do as well, but I have to double check. They're expensive, and again, most people just say, oh, the heck with it, I'll just buy the movie instead of burning a copy. Or you just get a digital copy and then you're good. Anyway. Okay. I mean, I guess the only other thing that we have to think about is using a mirror to focus light. So the whole idea is to manipulate light in order to get it into focus. And so I like thinking about triangles, and a lot of this geometric stuff is just thinking about triangles, in my mind. Okay. So, for example, if I have a beam of light coming in and striking this mirror, again, another exercise, where's the reflected ray going to go? Just ballparkish. Up, right? You can visually draw in a normal, and you say, okay, well, this one's going to be reflected up. Boom, you're done. Okay. So the second question, let's say, for example, I have this triangle, I have two beams of light. Let's say I have multiple mirrors. I just give you this just for, purposes of seeing what it looks like. So let's say I have beam 1 and beam 2, and you have a couple of these mirrors. How would you arrange these mirrors so that the beams actually cross each other? How would you orient these mirrors so that beam 1 and beam 2 would actually cross each other? Okay, fine by me. Right, something like this. You didn't see my slides earlier, did you? Oh, okay. You haven't broken into my office? Oh, yeah, okay, yeah, like the little, okay, yeah, nice. Yeah, they make like board games out of these where you're like, yeah, okay, yeah. So yeah, something like this. If I orient these two mirrors, I get those two light beams to cross, and boom, I'm done. Now, preaching in the choir. All right. So that one's, okay, we got that. So let's think about three triangles here. So you can orient these triangles to get the light beams across. We'd say that that's coming into focus. The location in space where we get all of our light beams across is called the focus. So next question. How about this? If I have three different mirrors, and I've angled them A, B, and C, which one will give you the largest deflection of the incoming ray? That's another question. So I've got a ray of light for each of these three mirrors. Which mirror will have the largest reflection, or excuse me, deflection with respect to the incoming beam? Just out of curiosity.
Should be the same.
Not the same. Yeah. Well, the incoming beam is going from from right to left. Incoming beam is going that way. Okay. Largest deflection would be, the largest angle from that direction. So if it's coming in this way, which one will give you the largest, change, deflection of the original path? I know I'm off today, but
So it'd be C.
it'd be C. Yeah, you get an idea. I mean, A, you might say, okay, well, I can draw in the normal, and okay, this one might go this way. It's a 90-degree deflection. Okay. Whereas B, it might be something like, okay, I got to draw in the normal. Might be something like this, right? Not less than 90 degrees. Incidentally, you could think of taking a dashed line and saying, okay, well, this is by how much it's been deflected. So the reflected angle would be with respect to normal. The deflected angle would be with respect to its original path. Might be, yeah. So C, well, the normal is more like this, and so you're going to get something, coming off like greater than 90 degrees. So we've got this idea that the angle in equals the angle out, and as we tilt the surface of the mirror, you can get greater or less deflections of the original beam. And that's about all we need in order to focus light. Okay. Something like this, Hey, let's say now I have multiple, I said beams of light. You could also call these multiple rays. Okay. So say I have light, multiple rays of light, and I want to get all 4 of these rays to meet, to physically cross at the same location in space. Okay. Good so far? And let's, where do I want them to meet? Let's say I want them to meet somewhere up here. Yeah. Which beam has to have the largest deflection? If I want them to meet somewhere, say up here, which beam has to have the largest deflection with respect to its incoming position?
Top right.
The top one, right? If I want it to meet, say for example, if I want these beams of light to meet, say right here, this top beam has to almost be deflected 180 degrees. Whereas as I move further and further down, this one might only have to be deflected, I don't know, what is that, 135 degrees. I'm just ballparking, spitballing. This one maybe only has to get deflected, I don't know, 120 degrees, et cetera, et cetera. As you move further and further down, those beams of light have to be deflected less and less. What can you tell me? Now, of course, I want to use mirrors to do that. What can you tell me about the mirror down here as opposed to the mirror that I have to put right here? Which one's going to be, I don't know, for lack of a better term, I'll say more vertical? Which mirror has to be more vertical? The one that I place down here or the one that I place up there? I'm sorry?
Up there.
Up there, right? I have to have it more vertical closer to the top in order to get a larger deflection. That's what we saw over here, right? The more vertical the mirror, the more the deflection. So you can imagine if I have light smeared out over an area, the further towards the edges, the mirror is shallow. The closer to the center, the mirror is more vertical. And so you can get kind of the fact that, hey, there's got to be this general shape to the mirror, this curved surface. Let me go ahead and get this out of the way, because I know I animated it. There we go. You get like a curved surface, something like this. So that further away, smaller deflection to get it up there, closer to the metal, larger deflection. Will this cause the beams to intersect or not intersect? Survey says intersect, right? Because let's see, I always get these, you know, I shouldn't, but for some reason I always get concave and convex confused. This is a concave mirror. Yeah, cave, that's exactly what I was remembering, yeah. So the mirror is caved in, and so they will eventually cause the reflected beams to intersect at some location, which we call the focal point. You don't get this focusing of light unless you have just the right shape, right? A flat mirror won't focus the light like a curved mirror will. And that in part is because of, you know, reflecting these beams that are far away towards the focus. Sorry, I keep saying far away. The technical term is the further away from the optical axis, the less steep the mirror needs to be. We'll have to talk about what's the optical axis, the center of the mirror. The further away you get from the center of the mirror, the less steep the mirror has to be. I don't know. Try it at lunch with a spoon. If they're shiny enough, I don't know how shiny the spoons are.
Like the same thing with glasses, they still go through it.
Yeah, we'll do the same thing with lenses. Yeah, but you're right, that the light, instead of reflecting off, the light goes through. We have to be a little bit more careful about how the light goes through, but yeah.
There are like Lord of the Flies, that you just take these glasses to set fire.
Oh, yeah. Didn't they kill Piggy at the end?
Yeah.
Yeah, poor guy. It's been years, and I just remember Piggy dies at the end.
I think Simon does too.
Does Simon?
Yeah.
Okay. Yeah, I gotta reread this. It's been years. I remember like the depravity of humans, right? You leave it. I just watched Wonder Woman 1884, and I'm like, oh yeah, humans make poor decisions when given free will. I'll have to go back and read. Now I'm gonna have to find my copy. I think I should read it to Graham. Cassie's like, no. Yeah, so that's what happens with your concave and convex mirrors. Now we'll have to talk a little, don't worry about, we'll have to talk a little bit more about how to actually get the focal point. The first thing I just want to say is, hey, the focal point exists. This is how it happens, right? You use the angle of the mirrors to reflect light and manipulate it to a specific location in space. And yes, you can have a concave or a convex mirror. Those will provide different kind of things. So we'll talk about that. Namely, I say different kind of things. What we'll find out is one of the differences between these two are whether you get a magnified or a demagnified image. So does your image appear larger or smaller at the focal point? That's one thing. The second thing that we'll find out is it going to be inverted or upright? It's not by accident that when you go to a convenience store, it's not by accident that they use a convex mirror. Namely, because it gives them an upright image and it's a demagnified view. Whereas if you use a concave mirror, go to the CC and use a concave mirror on the inside of the spoon, you'll notice that you have to, it's magnified first of all, and recollection is, it's going to be upside down. It might be upside down depending on where you're located. I think it's upside down, right? You get close enough, everything's inverted. To double check that. Maybe, oh, let me think here, okay. If you're far enough away, everything's upside down. And as you go in, it becomes right side up. We'll even talk about what happens there. Okay. Or if you have, shoot, how do I phrase this without it sounding bad? I was gonna say, if you have a concave mirror at home, then you can try it. But namely, the place where I think of where you're gonna see a concave mirror, and I can't think of a better way of saying it because I think this is how it's marketed, but sometimes they market it as beauty mirrors. Is that right? Like the ones where you use them tend to put makeup on. I don't know if that's correct or not. Do you have one? Yeah. Those are slightly concave, and so it gives you a magnified image that's upright. But if you move it further back, you'll notice that it's upside down. Have you noticed this? I don't know. I know that I played around with tips at home, and I apologize for calling it a beauty mirror. That's the only thing I know it by. I don't know. But those are slightly concave, so if you move it back, it should be upside down. No? Have you ever wondered why that happens? You've never? Try it with the spoon at the CC, flip it around. You'll notice no matter how far you hold the spoon away, it never flips. It's always right side up. It's a convex mirror. You flip it around and it's concave, you'll notice that out here it's upside down. You move it in, it's right side up. Okay? So somehow it depends on how close or far away you are from the mirror. Okay, so right now we're not getting into why that happens, we're just saying, hey, there's a focal point. You gotta be really careful with these things. Sorry, I know I'm kind of introductories today. You guys ever heard of Hubble? Yeah, like the telescope. You ever hear of the Hubble disaster? No? It's always a good life lesson. So if you're interested in the history of NASA or just good life lessons from science, here's a really good life lesson. You're probably familiar with the Hubble telescope. Developed in, what, about 1978 was, I believe, when Dow Corning, I think it was, started working on the primary mirror. Okay. So the primary mirror on Hubble is about 6 feet across. Now, of course, the whole function of a reflection telescope is that it uses the shape of the mirror to direct those beams of light across a 6-foot area to a single focal point. So you can imagine it is really important to get the curvature of that mirror just right, because you're collecting these beams of these light rays over a 6-foot area, and you've got to get them into a single point in space, which is where you set up your detector and your camera and yada, yada, yada. Incidentally, that's what your microscope does. When you're doing your focusing on a microscope, what you're doing is you're adjusting to get your eyepieces at the right focal location. Okay. So the mirror was developed, I believe it was manufactured in '78, and by about '84, the entire telescope was completed, ready for launch. Okay. '86. Of course, you're probably familiar with a disaster that occurred at NASA in January of '86. Late January, early February of '86. That was when the Challenger exploded. So Challenger exploded. It was a cold January morning in Florida, and what happened was there was actually icicles on the launch pad. The solid rocket boosters of the rocket were rated down to 50 degrees Fahrenheit. At the time of launch, it was 34 degrees Fahrenheit. So there's some interesting ethical studies, but essentially the engineer said, don't launch, the O-rings of the rocket boosters are rated down to 50 degrees. Incidentally, O-rings, they're made out of like a silicon or a rubber, and it gets really brittle when you make it cold. And so what happened was the joining seals of the solid rocket boosters got too cold, so they weren't flexible, and so they didn't seal tightly between the rocket boosters. So there's some other issues, but that essentially the engineer said don't launch. NASA says, can you prove to us that it's dangerous? The engineer said, we can't prove that it's dangerous. We can just tell you it's not safe. And NASA went ahead and launched. So it was a big coming to recollection moment. If you're ever interested, it's a really interesting case study of what not to do. The default is it's dangerous unless proven safe. No, it's safe unless proven dangerous. So there was a institutional change there. Any case, because of the Challenger explosion, Hubble was supposed to go up on a space shuttle. Incidentally, you don't send a one-in-a-lifetime telescope up on a shuttle that you don't think is safe. So Hubble went into storage for almost, I want to say it was about 4 years, to the tune of something like $1 billion. Because unfortunately, Hubble required a clean room, and also it was designed to operate in space, which means that it wasn't designed to sit in Earth's atmosphere too long. So it was a clean room, but they had to constantly purge it with nitrogen gas in order to keep it clean and all that kind of. It got rather expensive really quickly. I think it was something like $30 million a month, something like that, about $1 million a day. So I'll have to double check on that. In any case, about 1990, the space shuttle program is back on its feet. Hubble gets launched, it's in space. So you've already suffered a 4-year delay after 6 years of construction, 6 or 8 years of construction. And they opened it up, and one of the first things that you do with the telescope is what's called first light. You want to figure out how nice the optics are in the telescope. Okay? You want to test the quality of the mirror, in other words. So what you do is you find a really distant star, a star that looks like a pinprick of light, a point source. And you run it through your telescope, and then you see how good the image is on the other side, how blurry it is. Okay? So this is one of the images of the first light of Hubble. And this point source, you notice that's the dot in the middle. That's supposed to be a single dot of starlight. And you notice that it spans about 1/3600th of a degree. Which is pretty good. Right? That doesn't seem too blurry. Right? 1 degree divided into 3,600 segments. You know what the problem is? Oh, you probably don't know what the problem is. I'll tell you what the problem is, and this is the Hubble disaster. Hubble was not designed for 1/3,600th of a degree. It should have given resolution that was 10 times better. So after 8 years of development, a 4-year delay, you do your point source and you realize that you're 10 times worse than what you should have been. Right? In fact, this is some of the images. This is after they corrected the problem. Okay? What happened? Back in '78, when the mirror was being ground, okay, I said again, you have to be really careful. It's a 6-foot mirror. Okay? And so you have to be very precise on the measurements. Well, at the time, the company, I think it was Down Corning that was producing the mirror. I'll have to go back and double check. Or it's a company that was eventually bought by Down Corning. I don't remember for sure. What happened, though, was as they were grounding the mirror, this wasn't the first time they'd done it. They had instruments to measure the curvature of the mirror. What they had, though, was an old instrument that they used to use, and then they had their upgraded, newfangled instrument. And guess what happened? They measured the curvature of the mirror using their old, less precise instrument, and that instrument said that the curvature of the mirror was wrong, that there had been a manufacturing error, that it wasn't exactly the right shape. They took their newfangled, more precise instrument, and they measured it, and their newfangled, more precise instrument said, life is good, everything's fine. So they had 2 measurement apparatuses that didn't agree. You, as good scientists, what should you do? If you have 2 measurements that disagree, 2 measurements of the same thing that disagree, what's the first thing that you should do? Retake the measurements What happens if they still disagree? Figure out the problem. Why do these two measurements disagree? And, I mean, remeasuring is part of it. Did I just do a measurement problem? But then it's figure out the problem. Why do these two instruments that should agree not agree? Guess what they did? Rock, paper, scissors, I love it. That's an old, less precise instrument. Surely our new, fangled, more precise instrument's the correct measurement. Right? Oh, that one's old, it can't be reliable. This one, it must be the right measurement. It turns out that was the problem. There was in the measurement apparatus, there was a layer of paint somewhere that shouldn't have been. And because of that single layer of paint, you know, on one of the components of this newfangled instrument, the mirror, the 6-foot mirror, was off by like the width of a piece of paper on the edges. And that was enough to blur the image out of specs. When you have two measurements that disagree, figure out what the problem is. Do the remeasurement, make sure it's not human error. Right, that's the first place to look. But then if they still disagree, you got to figure out the problem. Otherwise, you launch, you know, I think this is like $4 billion. I got to double check. I think it was $4 billion after storage and everything like that. Double check me. I can't compete with Google. Okay? But it was a huge amount of money. They get it up into space after 15 years, and they find out that the image is blurry. So one of the first things, this is in 1990, so NASA gets this, it's a huge embarrassment, they have to figure out the problem, they finally figured out what was the problem. The only upshot, the only silver lining here is that the mirror was misshapen, but it was consistent. They knew exactly how off the mirror was. So in 1992, the first servicing mission, they did some corrections to fix the image problem. This is still, even the images that you see today from Hubble are not as high of resolution as what it was designed for. They're still, I think that instead of being off by a factor of 10, it's off by like a factor of 2 or 1.5 or something. Yes?
I feel like when NASA lost like their orbiter because they got converted to SI.
Yeah, that's back in 1998 or 99. Yeah, like just every once in a while. That was actually the contractor's fault. That was the subcontractor's fault. So yeah. So this happens every once in a while, but this was back in like 1990. 1992, they managed to rectify the problem, and then since then, Hubble's been working fine. It's just a shame because all those beautiful images you see are still like, they're out of focus just ever so slightly. So you gotta be careful with this mirror stuff. So this is the big, I mean, somebody lost their job over that one, let's be honest, right? Like, there's a lot of people that lost their jobs over that. Make $50 mistakes, not $1 million mistakes. Or $125 million mistakes in the case of the Mars Climate Orbiter. Hey guys. That's all I have to say about mirrors. Now you can impress your family and friends with that. Hey, remember the Hubble disaster? Hubble disaster? Yeah, you know the misshapen mirror in 1978? What? You can go and impress your friends with this. Okay. So that's all I have to say about mirrors. We'll come back to the mirrors when we do what's called ray diagrams. So I'm going a little bit out of order. I said, okay, I'll talk about the mirrors and the law of reflection. I'll talk about lenses and the law of refraction. Then we'll go and say, okay, how do we qualitatively assess mirrors and lenses? And then after that, we'll quantitatively assess mirrors and lenses. And incidentally, after you can qualitatively assess one mirror, you can basically qualitatively assess a bunch of mirrors. Or after you can do one lens, you can basically qualitatively assess a bunch of lenses. All right, so you string them together. So when we're dealing with lenses, basically lenses work off of something called Fermat's principle. I think it was French, so you don't pronounce the ending, right? French syllables, like you just drop the last syllable. Right? It just doesn't exist. So it's not Fermat's principle, it's Fermat's principle, if I recall correctly. And you're probably well aware of Fermat's principle. Okay? When I built this slide when I was back at Purdue, yes, I reuse stuff. Should yell at me sometime. But I thought it was a very convenient situation. So it doesn't apply here at Hanover. Unfortunately, I tried. It doesn't work. But when I was at Purdue, Purdue's down in Lafayette, or up in Lafayette, if you're familiar. So if you head up 65 and then 69 towards Chicago, or 65 towards Chicago, excuse me, you eventually run across Lafayette. You know, there's a nice Starbucks there if you ever need a drink. So there's Lafayette, and at the time, where I originally grew up is in northern Michigan, right here, Manistee. And I was always faced with this weird decision, because when I would go and travel up to Manistee, there's two situations. One of them was I could actually take this route to Gary, Indiana, and then shoot up the coast to get to my house. Well, my mom's house, yeah. Home, but not really home. Like, you find out after a couple of years that home isn't really home anymore. You know, you go home and there's a hot tub room, and you're like, this isn't home anymore, right? So one of them was always this, you know, you head up 65 to Gary, Indiana, and then along the coast. But then there's always another one where I could actually just head straight north to basically South Bend area and then do my trip. I was always faced with this weird debate, because the issue is that if I actually check this, what do you notice about these two routes? Or if you had to drive this, what would you do? Which route would you take? It's okay, don't be shy. Which route would you take? Just based on this information.
The one that takes less time.
The one that takes less time. Okay. Why?
That's the point.
That's the point. You want to get home as fast as possible. I will choose the route that takes less time.
I would do the one that takes less mileage.
Yeah. I mean, but most of us, I think, by and large, most of us would take the one that takes less time. I agree with Isaiah only because I hated the 65 route between Lafayette and Indiana, or Gary. It was just too busy. Like, this is just country back roads, so you get that wonderful hog smell for like 40 miles. Yeah, most of us would take the one that takes less time. That's the whole point. You notice, though, that the route that takes less time is a longer distance. Right? If I almost, 30 miles? 20 miles. Even though it's 20 miles longer, it's almost 20 minutes or 10 minutes faster. You have just applied Fermat's principle, except for Isaiah. It's okay, I'm with you. Fermat's principle is simply this. Light will not travel the shortest distance. It will travel the shortest time. Light will not follow the route of shortest distance. Light will follow the route of shortest time. That's all that Fermat's principle says. And again, it's hard to find like Hanover, if I do it, there's not two routes to my parents' house. So it doesn't work here at Hanover, but it just happened at Lafayette, there was a situation where it did work. The longer distance was the longer distance was the shorter time. And you know why, it's highway, right? Like, I can do 70, so I can make up the extra distance. Okay. So Fermat's principle, light will not follow the shortest distance, it follows the shortest time. And from that, we could at least get a qualitative understanding of what's referred to as Snell's law. So you okay with Fermat's principle? There's a cute video, I'll have to find it at some point. I'll see if I can find it, it's a funny one. It's a video about how good dogs are at math. In fact, it's a video proving that dogs are better at math than people. Okay, and I mean, it's kind of funny, but what they do, they throw a stick in the water and they tell the dog to retrieve it. You know, you're playing fetch. And you know what the dogs do, most of them? They'll run along the beach, and then at some point they'll turn and jump in the water and swim after the stick. The reason for it is because even though it's a longer distance, they're faster running on the ground than swimming through the water. And they recognize this, so they run along the ground for a while, and then they jump in the water. Guess what the person did? Went straight into the water. Their analysis concluded that dogs are smarter than people. All right, yeah. So, shortest distance isn't shortest time. Okay, so here's the situation here. I've got two materials. And so I've got a material that I've labeled as V1. What I mean by this is, in material 1, light travels at a speed V1. At material 2, which I have over here, light travels at a different speed. Okay? So I have two materials where the speed in material 1 is greater than material 2. Okay? In which material would you want to traverse a greater distance? If I try to go from this dot to that dot, in which material should I travel a greater distance? What's your gut tell you?
Traverse, just mean travel.
Travel through. Yeah, excuse me. Traverse, travel through. You want to travel a longer distance in material 1 or material 2? Material 1, you can travel faster in material 1. I should travel a longer distance in material 1. So rather, I mean, you can kind of see this. If I go straight line, there's some sort of optimization. Right, if I travel the same, there's some, let's see here, let's find the mouse. There it is, right there. There's some sort of optimization. Okay, well, okay, that's not very optimized in terms of route. Let's try that again. All right, if I just go straight, there we go, something like this. I travel the same distance of both materials. That'll give me some time. If I travel a slightly longer distance in material 1, I'll decrease the time. I don't know by how much, but I know that if I travel faster in material 1, I can get a slightly less time. So what that means is that you end up, this is exaggerated for viewing purposes. And again, we don't know how far, we don't know what the optimal time is. You know that eventually if you travel too far in material 1, then your distance is too large and then your time goes up again. Right? If I travel all the way to Chicago on the highway before I go back up the lake shore, then the time's going to be larger. Right? The increased distance isn't offset by the faster speed. Somehow light knows this automatically, which is a really cool and wonky thing that Einstein comes up with. Okay? The technical term is light travels along a geodesiac. What he means is the shortest path in time. It's a fancy term, geodesiac. Geodesiac. It's the same. Anybody fly to like Europe? I guess this is another example. You ever been to Europe, or I guess Asia, or what path did your plane take? Or where'd you leave from? Where'd you land from? Do you know what you flew over?
I was 11, so actually, I don't know.
Oh, okay.
Sorry.
Oh, nice. Where'd you go?
Poland.
Poland. Cool. Warsaw? Or did you land in Warsaw and then travel around, or?
Yeah, we landed in Warsaw.
Okay. So you probably left from like Detroit, or were you still in the Midwest, or were you in like East Coast, West Coast? Okay, Chicago, let's say Chicago to Warsaw isn't that out of the question, right? Okay, so we'll say Chicago to Warsaw, although maybe it was Chicago to Atlanta to Warsaw or something. That's okay. We'll say Chicago to Warsaw. Okay. And then this is the same thing. I flew from Detroit to Paris. Same thing. And you know what? Most of the time, flights to Europe, you know where they pass over? Usually Canada and Greenland. Because the issue is, again, if newsflash, the Earth is round. Yeah. And if you're traveling from something like Chicago to Warsaw, this distance around is longer than going up and over the top. sometimes, in fact, airlines usually do this. They're called great circles. Great circles. Instead of flying at a constant latitude around, they'll go up and over the top, and it's a shorter distance. Also gives you a shorter, and for the case of planes, it's also a shorter time. Anyway, light does the same thing. So if you ever wonder, why is the light not going in a straight line? It's because going along the curve is better. Which gets you into all wonky YouTube videos. All right. No, Corey's like, no. No, you don't get excited about curvature of space-time? Yeah, okay. 225, next semester, fall. I'll see you there. I'll sign you in if I have to. Okay. Next question. So, traveling faster in material 1 than material 2. Because of that, you travel a longer distance in material 1 than material 2. That's to minimize the travel time. What can you tell me about the angle with respect to normal? Okay. So for example, compare the two situations. V1 is equal to V2, and I have the angles being the same. What happens when V1 is greater than V2? How does the incoming angle and the outgoing angle compare? I probably already gave it away in the last slide, but hopefully you didn't remember it. Go ahead, talk to your neighbor, give me an idea. As the speed in V1 increases, right, as speed in material 1 increases, how does this angle compare to that angle? Go ahead, give me an idea. Yeah, talk to me to get an idea. I'm going to see what I put up on the next slide. Okay, yeah, good. You know what happens as the speed of material 1 increases, you want to travel more distance or less distance in V1, in material 1? More. Which means you could think of this point, instead of it being equidistant, you could think of that intersection point as being down here. So what can you tell me about the angle theta 1 as compared to theta 2? We could draw it in. Let's see. So we do something like this, and then something like this. There we go. Which angle is bigger? Theta 1. Don't forget, you're measuring with respect to normal. Okay? So you could put in a line, and this angle is going to be greater than this angle. As the speed of material 1 increases, the angle in material 1 also increases. I'm just trying to give you some sort of, I'm giving you a heuristic argument here. How does the speed of light in a material change the angle? And this is called the angle of refraction. When light is traveling through a material at one speed, and it hits a material where it travels at a different speed, it will also change the angle it's moving at. Part of that is because it's shortest time, not shortest distance. we got an idea here. As the speed goes up, you know, the angle that it makes with normal goes up. And I should say that the theta 2 goes down. Right, so we had that theta 1 gets large, theta 2 is small. Now I'll give you the qualitative or quantitative relationship. It's known as Snell's law. Okay. So yes, we could keep going. We could derive this whole thing. It's basically triangles and yada, yada, yada. But I'm not going to do that. Relates the speed of light to the angles. And here it is. Boom. You say, but wait, Greg, where's speed? I need to give you another definition. Okay. The speed of light is implicitly in here, and it's in that little n. You might have already run across little n in terms of refraction of light. Physicists are very creative with their names. Little n is referred to as the refractive index. It is a measure or index of refraction, might be another term. It is essentially a ratio. It is how quickly does light move through the material as compared to how quickly it moves through vacuum. It's a ratio. Let's put that up there. N is defined as speed of light through a vacuum divided by the speed of light through the material. What's the smallest value of n possible? I should ask you that. 1. Good. And the index of refraction will always be greater than or equal to 1. For the purposes of this class, for the purposes of optical light, index of refraction is always going to be equal to or greater than 1. Or in other words, light slows down as it travels through a material. In vacuum, it travels at the speed of light, c. If it's in any other material, such as glass, water, oil, etc., it slows down. It travels slightly slower. I think the index of refraction for water is 1.3, if I recall correctly. So that just gives you a sense of how much slower it travels. Hey, we'll pick up there on Wednesday. Thanks for your attention.